have discovered a new superconductor. It's not just any material. This one is easy to produce, cheap, and it has some pretty incredible properties. And the best thing about this new material is that it allows scientists to do something they thought was impossible. Let's take a closer look. When we think of superconductors, we think of materials like niobium or tin. These metals become superconducting at very low temperatures, below 2 Kelvin in most cases. At these temperatures, they conduct electricity without losing any energy and also repel magnetic fields. But being at such low temperatures is really expensive and impractical for most applications. That's why many people were excited when LK99 was synthesized in 2020. It became the first ambient temperature superconductor if it turned out to be true. LK99 was synthesized by a group from the Korean Institute of Science and Technology. They published their results in a preprint and claimed that LK99 becomes superconducting at 127 Kelvin. However, other groups tried to reproduce the result, but failed, so it doesn't seem that LK99 is an ambient temperature superconductor after all. But maybe it's because they used the wrong recipe. After all, we know quite little about how to make good superconductors. For example, we don't really know what makes cuprates superconducting. Cuprates are probably the most widely used superconductors because they can easily be processed into thin films, but they still require temperatures below 100 Kelvin. The thing with cuprates is that they are ceramic materials. Their crystal structure consists of copper oxide layers in between, which there are other elements. We call these elements the rare holes. It can be, for example, yttrium, barium, calcium, or even silver. We use these rare holes to tune the material's properties. For example, the cuprate material YBA2Cu307_delta becomes superconducting at 92 Kelvin. But we don't understand why exactly this combination of elements at this precise concentration of oxygen makes it superconducting. So we don't really know how to search for new superconductors, but physicists have some good candidates. One promising route is the so-called iron-based superconductors. The first material in this class that became superconducting was LiFePO. It needs to be at about 80 Kelvin. But iron-based superconductors have the advantage that they can be tuned to higher temperatures by applying pressure. For example, researchers managed to make iron superconduct at room temperature and ambient pressure by putting it inside a hydrogen cage. But the problem with these materials is that they don't become perfect conductors. That means that there's a small amount of electrical resistance, and this resistance increases at temperatures above 60 Kelvin. So it's difficult to find the optimal balance between a low critical temperature and a small residual resistance. This brings us to the new paper. The authors have created a new material that combines the best of two worlds. It's based on thorium and iron, and they can tune its properties by substituting some of the thorium atoms with yttrium. The resulting material is called TH1_XTX. The X represents that we don't really know the exact concentrations. The researchers first created the material as a powder, and then they pressed it into a thin plate. They found that for X equals 0.4, the material becomes superconducting at 100 Kelvin. But the cool thing is that this superconductor has no residual resistance. Usually that's mutually exclusive. If you want to have a material that has no residual resistance, then you need it to be a bit warmer. And if you want it to be warm, then you usually get some residual resistance. Here both problems seem to be solved. I have to admit that I think it's likely that this result will not be reproduced by other groups. That happens quite often with preprints, but this time I'm not so sure. That's because the authors also present neutron scattering data. That's a standard measurement to check whether your material has magnetic order or not. Magnetic order typically destroys superconductivity. So if you want to have a good superconductor, you need to make sure that there's no magnetic order. In this case, the neutrons show that the magnetic moments of the iron atoms form a helical structure. Interestingly, this magnetic structure is similar to that of chromium, which is not a superconductor. But the good news is that they found no evidence for magnetic order in the thorium-iron part of the material. And this could be the reason that it's superconducting. So far, the sample they created is only tiny, 0.8 by 0.6 by 0.4 millimeters. So we don't know if the superconductivity will disappear if you scale up the production. Also, the material might be slightly contaminated with other stuff which helps superconductivity. It's very common to add small amounts of impurities to enhance the effect. However, if this material turns out to be a true superconductor, then we have two big advantages. First, we know that iron-based superconductors can be turned into better conductors by applying pressure. So it should be possible to further increase the quality of this new material. Second, thorium is much more abundant than niobium or tins, so this material could be produced at large scales for relatively little money. There's still a lot that we have to learn about this new material, but it shows that the research into new superconductors is going in the right direction. So what's the use of better and cheaper superconductors? Well, we use them, for example, in nuclear fusion magnets. We've talked about that before. Fusion magnets need to produce enormous magnetic fields, and it has to be done with superconducting wires. Currently, we use niobium tin alloys for that purpose. The European company Furukawa produces these wires, and here's an interesting fact that I learned from them. These wires are so thick that they must be produced in 2 steps. First, they draw the wire into a thick strand, and then they pull it into a thin strand. The second pulling process is done with a special machine that's called a universal pulling machine because it's used everywhere where wire drawing is needed. This machine has a big advantage over regular pulling machines because it can measure the wire's diameter while pulling it. That way they can keep the diameter of the wire as constant as possible. You see, it's important that the diameter of the superconducting wires is the same across the whole coil, because otherwise the current will concentrate in the thinner parts and heat up. Anyway, once we have better and cheaper superconductors, it should be easier to build bigger and better fusion magnets. This in turn would help us to reach ignition and produce net energy gain. Another application of superconductors are quantum computers. In this case, we need single photon detectors that convert a single photon into a current pulse. That way we can count photons, and that gives us information about what the quantum computer is doing. These detectors are made from superconducting materials. Better and cheaper detectors mean more accurate measurements, and that in turn means a better and faster quantum computer. And finally, there's medical imaging. There are some techniques that use superconducting materials to image the inside of the human body. This is particularly useful to study blood flow in the brain. The resolution of these devices is limited by the size of the superconducting material. So if we had better and cheaper superconducting material, then we could make smaller and better sensors. To summarize, better and cheaper superconductors would help us in nuclear fusion, quantum computing, medical technology, and many other areas. So let's hope that this new material turns out to be a true superconductor. Thanks for watching. See you tomorrow.